We now move to session 2, which includes a presentation and demonstration by Dr. Faizan Sayed. Dr. Sayed is a dedicated researcher in medicinal and pharmaceutical chemistry, specializing in computational drug design, synthetic chemistry, and biological evaluation of novel therapeutic agents. His expertise spans medicinal chemistry, parallel synthesis, synthetic organic chemistry, ADME studies, and QSAR, enabling him to apply a comprehensive and integrated approach to modern drug discovery. He earned his PhD from JSS Academy of Higher Education and Research, Mysuru, where he conducted impactful research leading to publications in reputed scientific journals and the filing of a patent for an innovative therapeutic formulation. Dr. Sayed is highly proficient in computer-aided drug design tools such as Schrödinger and BioVia Discovery Studio, and experienced in advanced analytical and experimental techniques, including LCMS, MS, and HPLC. I invite Dr. Faizan Sayed to present the fundamentals of generative AI, ultra-large molecular docking, scaffolding hopping, and AI-based prediction of ligand-protein interactions. Dr. Faizan, you're muted. We cannot hear you. Dr. Faizan, we still cannot hear you. You are not audible.
Then you have to unmute, I think so. We are not able to hear you still. No. Anbu, if you are there, can you help him? Check it. Just see the button,
Hello.
like whether organizers has given the permission to. I think you might have given the permission, but like okay, check whether the is my problem or
Am I audible now?
yeah. Yes. Go ahead.
Yes, we
Okay.
can hear you, Dr. Faizan.
Okay. 1 second. And I hope my screen is also visible.
Yes.
Yeah. Thank you so much for the introduction. So I'm Dr. Faizan and I works as application scientist at Molecular Solutions. And in this presentation, I'll introduce the fundamentals of modern hit discovery using the SeeSar, showing how the protein ligand interactions can be analyzed in clear and interpretable way, and how the ultra-large chemical space docking can be explored efficiently to identify the high-quality hit molecules. So here's the agenda of today's session. We'll quickly overview the structure-based drug design. Then we'll go for the introduction of SeeSar and chemical space docking, followed by the demonstration. So as all of you are aware, drug discovery can be broadly approachable for the molecular design in two different ways. First, we have the structure-based drug design, and then we have the ligand-based drug design. So, in the structure-based drug design workflow, it mainly depends on having a protein structure available. So first we select the disease target, then we evaluate whether that site is even druggable or not. Once we know where we can, you know, dock our molecule, then we can go and further predict the interactions and refine them to improve the affinity and fit of the molecule overall. And all of these tasks, from binding site detection to post refinement, can be efficiently carried out using SeeSar, which is the software that we use on the structure-based drug design site. So let us now see what's inside the SeeSar. So it comes with a complete set of integrated modules that covers almost every need in the structure-based and ligand-based drug design. So many of the algorithm and the scoring functions like FlexX, hide, FlexS, and FastGrow, these can also be run from command line on a computer or a server or cloud setup. So let me quickly walk you through each working mode, and you all need to pay attention towards all these eye-catching icons because they will be your roadmap to navigate the entire software. So first we have the protein mode. So in this mode, you can simply drag and drop your protein from the online database like PDB, and within second, SeeSar prepares the target and you can immediately start working with it. Then we have the protein editor mode, and using this mode, you can refine your protein structure, you can explore the rotamers, you can also introduce the mutations into the protein or adjust the side chain based on your hypothesis. Then we have the inspirator mode, and this is one of my favorite mode. This is the ideation powerhouse, and within one single click, you can explore the scaffolds, you can grow the pocket into the molecule, you can change the R group, you can merge and link the molecules, and all this is possible because of the algorithm that we have Recore and Fast group behind it. Then we have the docking mode, and within one click, you can dock compounds, whether it be standard docking, template-based docking, or covalent docking. All sorts of docking are supported with the SeeSar. And then we have the chemical space docking, and this allows you to dock not just thousand, but billions or even trillions of molecules through highly optimized structure-based screening. Then we have the binding site mode. So using this, you can detect binding sites, expand them by adding individual residues, or you can identify new empty pockets which are available in the protein. Then we have the protein editor mode. So here simply you can modify the molecules in the 2D or 3D, and directly from there you can take it in your workflow for docking or inspirator mode. Then we have the analyzer mode, and this mode visualizes the height-based affinity scoring functions. And sorry, and it basically filters your molecules, like in case if you have tons of data, like 50,000 poses, you can simply filter it out using the analyzer mode. One second.
If anybody has questions for Dr. Raghu or Dr. Faizan, please be sure to write in the chat. Thank you, everyone.
Yeah, I'm sorry. Ah, huh. Yeah, if you have any question, you can ask me, or else we can continue now.
Yeah, go ahead, Faisal. Yeah.
Yeah. Also, we have the similarity scanner mode, and with the Flex S algorithm, you can simply align your molecules in the 2D, and directly from there you can design the molecules without even need of the protein structure. So before moving ahead, I just want to mention that SeeSar is built on three core principles. So first, it is very fast. You can instantly understand your protein ligand interaction. Within one glance, you will be able to understand where the atoms are, you know, not having good interactions, where good interactions are there, and where the place for improvement is there. Second, it is quite visual and with the color codes and everything. And third, it is easy to use. So the clean interface which the SeeSar is having, it makes it effortless for both the new users as well as the experienced modelers. So together with this fast visual and easy workflow, you can interactively do your uh, designing of the molecules and with better scoring and smarter decisions. So in this slide, we'll focus on the algorithm behind our docking, that is the FlexX. So FlexX predicts how the small molecules or the ligand binds to the active site of the protein. So what sets FlexX apart is its incremental construction algorithm, which allows it to perform docking both accurately as well as quickly. So let me break down this algorithm and show you how it basically works. So the first step in the mechanism of this FlexX is fragmentation of ligands. So the ligand is first it is first splitted into the smaller fragment. So now you can imagine it as a Lego toy. So when you disassemble that Lego toy, you come up with a single building blocks, isn't it? Single piece of Lego. So similar way, the fragmentation of ligand in the binding pocket takes place. Then comes the first or the initial placement. So once one fragment or a combination of fragments are then placed into the multiple possible positions into the binding pocket, then the pre-scoring happens. So whatever the initial placements of the fragments happen, we'll do the pre-scoring and quickly evaluate the fast using the fast scoring method. And here itself, the poorly fit fragments will be eliminated. Then comes the in, then comes the incremental buildup, and the ligand is then again reconstructed step by step, adding the one fragment at a time. Then we have the iterative scoring, and with each step, the partial solutions are there compared, and only the best scoring conformers are kept. Then the final output, whatever all the fragments are assembled, the top scoring and binding modes are provided and predicted using the docking poses. So in the last slide, we have seen the algorithm. Now we'll see the scoring function behind our docking. So as I mentioned earlier that our software SeeSar is very visually strong. So with one glance itself, you will be able to understand what's happening in the interaction of your ligand into the binding pocket. So the first key element that we have behind the scoring is hide scoring. So hide is thermodynamics based scoring function that evaluates the hydrogen bonding and dissolution. So here you will be able to see with the height scoring, uh, every atom in the ligand will be accountable for its scoring. So each atom is in the ligand is color coded to show you how it is contributing into the binding pocket. So with the single glance, you will see where the ligand is hurting or where the improvement can take place. So here you will be able to see the spheres. We call it as coronospheres. Some are green in color, and here one or two, these are red in color. So green coronosphere represents that favorable binding towards the uh, receptor, whereas red represents the unfavorable binding. So within one glance, you will be able to understand which atom is helping in the binding affinity. If not, then you can replace those atoms and you can modify your molecule. Then second, we have the molecular torsions. So SeeSar evaluates these molecular torsions using the traffic light system. And these are derived from the statistical analysis of the crystal structure database. And after seeing this, you can instantly understand where the torsion angle is favorable in the molecule or where it is strained or where it is unrealistic, so that you can design your molecules with much more confidence. So let us now see the docking mode. So in the SeeSar, it helps you quickly predict how your ligand binds with the target site, and you can immediately judge the quality of each pose. So here also we have integrated the traffic light system for covering the clashes and for torsions and height-based contribution, which gives you instant visual understanding of the complex. And to guide your search, you can apply pharmacophoric constraint to control your uh, conformers. So SeeSar also prepares you for variety of project needed. So besides the standard docking, we also have the template-based docking and covalent docking. And finally, the streamlined compound handlings let you quickly evaluate the key post parameters and shortlist the most promising candidates to follow up with. I'll now discuss quickly about the covalent docking. Most of you might be aware of covalent docking. Can someone tell me what are the requirements of covalent docking from the participants?
Unless you are able to see the message.
Yeah, you can. No, I'm not able to see the message. You can
You can't see
unmute.
the messages.
Yeah, I cannot see the messages.
Yeah, you can just continue, and then we can take the sessions afterwards.
Okay. So, uh, so one of the main requirement for the covalent docking is covalent ready warhead and the receptor. So SeeSar automatically detects the most commonly used 36 covalent warheads in the medicinal chemistry. As you can see here, all the lists it is available. So during the run itself, it can automatically detects, and it means that you don't have to manually prepare your ligands or modify the structure. So once you select the covalently targetable residue in the protein, SeeSar simply evaluates the best possible poses. And most importantly, it evaluates all the potential stereoisomers, and that may result from the covalent reaction, again, making it ensuring that it is realistic and with a thorough assessment. So this makes the covalent inhibitor design fast, reliable, and easy to integrate into your routine workflow. And then we have the inspirator mode. So with it, you can generate the smart, chemically meaningful ideas within the single click. First, it supports the scaffold replacement. As you can see here in this image, one part of the molecule, specifically the core of the molecule, is faded in color, right? So SeeSar, using the inspirator mode in the SeeSar, we can replace the scaffold, and if you want to remove any undesirable core area, or you want to explore any novel chemotypes, within a click, Inspirator mode lets you instantly browse tens of thousands of high quality 3D scaffolds and find the novel alternatives. Second, it also enables the analogging. So based on your ligand and the binding site, into the binding pocket, SeeSar applies over 290 medicinal chemistry transformation to suggest promising modifications. And third, for the binding site complementation, it can screen hundreds of thousands of fragments and propose the extension that naturally fills the nearby binding pocket, often within the second. And for this, we have, you know, thousands of different fragment libraries coming from the Biosolve ITs. You can directly use them. So now let us slowly move towards the chemical space docking. And as you all are aware that virtual screening, we do the virtual screening uh, because it is one of the cornerstone of the modern drug discovery. And in the computational chemistry, we need to sift the molecules from the larger collection of the compounds and to identify the most likely molecules which binds to the biological target. And most of the time, this process is often visualized as a funnel. So here we start with a large library, probably million of molecule, and then we apply the successive filters such as docking, scoring, and property constraint. And with each step, the number of molecules or the number of compounds decreases, whereas the quality and relevance of those compounds increases until we arrive at a manageable hit of the experimental validation. And this approach has been extremely successful in reducing the cost and accelerating the early stage drug discovery. So, in classical virtual screening, the most commonly used approach is the docking based approach. So here each molecule from the pre-built library is individually docked into the target binding site, and a scoring function is used to estimate the binding affinity. So many of you might have used the tools like Glide, MOE, Autodock, and Pyrex, and they are widely used and adopted, proven extremely useful for the screening thousands to even million of compounds. And this brute force approach works well when the library size is manageable. Like if you are working with 1,000 molecules or 1 lakh molecules, or such a library which is manageable. And however, as the chemical space library continues to grow beyond million, the size of chemical space will explode. And then screening the molecules one after another will become a huge task, and which basically leads up us to an important question, that what happens when we try to apply the same brute force brute force docking strategy at much larger scale, like for millions or trillions molecule. What happens at that time? So traditional docking has been extremely valuable, but it starts struggling when we push it to larger scale, like for trillions of molecule. And that's where the chemical space docking comes into the scenario. So the chemical space docking is the new era of virtual screening. And this slides directly compares the docking workflow, traditional docking workflow, with the chemical space docking. So in this graph, on the x-axis, we have the number of compounds. And on the y-axis, we have the predicted binding affinity. So in the brute force docking, as we can see, the more compounds, uh, we usually see a downward trend in the brute force docking. So we proceed with much more libraries of molecules, but the number of high quality compounds does not increase with the steps. So most compounds scores poorly and we spend lot of computational resources, and in return we get a limited gain. So in contrast, we have the chemical space docking, and it shows a bell-shaped distribution. This means the method intelligently enriches for higher ranking compound instead of wasting efforts on weak chemistry. So this happens because chemical space docking does not blindly dock full molecules, but it starts from the building blocks, then focusing only on the chemistry that truly interacts well with the binding site. So as a result, we gain access to extremely large compound collection, and we can discover the novel molecules, we can discover the unlisted IPs, and most importantly, all the results which are coming out from the chemical space docking are synthetically accessible. You can directly order those molecules from the vendors. So before diving deep into the chemical space docking, we'll see what I actually mean by the chemical space. So here we have a table, uh, first having the compound library and the chemical spaces. So in the compound libraries, we are having the explicit list of molecules that already exist in SDF format, Mol2 formats, or Smileys. The same compound libraries, traditional libraries like ChemPL, PubChem, and all those things. But in case of the chemical space, it is fundamentally different. It is not enumerated list of molecule. Instead, it is defined by the building blocks and the chemical reaction rules. So the molecules are generated during the process, during the docking on the fly, and only when they are needed. So this is why the chemical space can easily reach tens of billions or even trillions or septillions of molecules without even storing all the molecules explicitly. And the compact dot space format, so unlike SDF or Mol2, we have here dot space format, which makes it computationally efficient, and most importantly, every molecules which is generated during the run, it is chemically valid. So now that we understood what the chemical space is, now let's take a look at the real spaces which are available commercially for us today. So at the top, you're able to see the make on demand spaces, and these are built from the validated building blocks. And you can see here the number 1.3 uh, million, 7.6 trillion, and all those. So these are built from the validated building blocks and the reactions, and you can typically order them directly from the vendors like Ambinter, Enamine, Voxy, Ottawa, and the ChemSpace. In the middle, we have a section called Do It Yourself Spaces. So where compounds can be synthesized in-house, like in your laboratory, or you can get it synthesized from the any third-party CRO company. And finally, we have the ideation space, and this is again coming from the Biosolve IT's knowledge space, which spans again trillions of chemically reasonable compounds. So all these chemical spaces are available for you, and you can dock your molecule, you can get the results of those, and you can shortlist the compounds and directly order it from these vendors. So this particular slide marks the conceptual shift from the traditional virtual screening, like traditional docking, to the chemical space docking. And I want to mention here one important point, that the chemical space docking does not change the science of docking. So the uh, underlying principle of the chemical space docking is exactly same that we do the Uh, we generate the ligand interaction poses, then we see those interaction and we do the scoring. So what change here is how the molecules enter into the workflow. So in the standard docking, uh, we rely on larger pre-enumerated libraries, which quickly becomes computationally expensive. But on the chemical space docking, the molecules are created on the fly, which are guided by the scoring function. And poor candidates are discarded early, while the promising candidates are then expanded. And this allows us to access trillions of compounds without explicitly docking trillions of molecules. And crucially, whether it be the standard docking or the chemical space docking, both these approaches use the same FlexX algorithm, which we have discussed in the earlier slide, uh, for the pose prediction and height-based scoring. So now let us see the interactive workflow of the chemical space docking. So now the question might arise that how do we explore trillions of molecules without docking trillions of compounds or without getting trillions of docking calculation? So here the answer is simple. We do it stepwise with the interactive workflow. And the first step of this workflow is anchoring of synthon. So instead of docking full molecule, we are starting with a synthon, which is smaller in size, less than 200 Daltons, chemically meaningful, and that contains the extension vector. As you can see here, this dotted circle, or here you are able to see here a blue vector, blue color atom. So this is the extension vector. So these synthons represents only a tiny fraction of the total chemical space. And we dock these synthons into the binding site using the same structure-based principle. The post generation takes place, and then scoring, and then we identify those high quality synthons, and we identify the productive interactions, and we further go for the next steps. So whatever the poorly interacting synthons are coming, so as you can see here, out of these four, two are accepted for the next step, whereas two are rejected. So here we can see these are coming from the height based scoring. So above two are accepted because they are basically showing good height based scoring, and the bottom two will be rejected. As you can see here, first molecule, first synthon is showing the unfavorable towards the receptor based on the height based scoring, whereas this particular synthon, it have the height based scoring properly, but for the molecule to grow, there is for the anchor, there is no much space, right? So this is again rejected because again it will bump the molecule into the walls of the binding protein. So we will move ahead for the first extension and the second extension using the accepted synthons. So once all these well anchored synthons are ready for the further steps, this first extension happens. So here all the chemically accessible compounds that can be built from the selected synthons are generated and then again docked. So importantly, these compounds are not pre-enumerated. Again, they are generated during the process only when they are needed. So because the weak synthons are discarded earlier, now we are working with high quality data, which again dramatically reduces the search spaces. And this allows the chemical space docking to screen what is effective for the entire chemical space using only the fraction of the computational cost. So again, after the first extension, the second extension step is applied, and then we finalize the molecule. And since everything is built using different building blocks and reaction uh, rules, which are already defined, every hit again, which you see coming out from the chemical space docking, it is synthetically accessible to you, or you can purchase them from the vendors. So again, we are having here all these three steps. So first, anchoring of the synthon that is happening. Then the favorable anchors will be taken ahead for the second step, and then we have the second extension from where we get the whole molecule. So the SeeSar comes with the GUI enabled setup with the visual inspection and quite user friendly intervention, which makes the SeeSar quite interactive rather than fully automated workflow. And also this approach ensure that efficient exploration of molecule or the massive chemical space happens while retaining control for the expert decision making. So quickly, I'll show you the success story. Here we have the publication coming from the Journal of Medicinal Chemistry, which is published by the AstraZeneca. Here the researchers have got the 43% hit rate. So they have synthesized 93 molecules from the chemical space docking, and out of those 40 molecules have shown better activity than the co-crystallized ligand. So, so the topmost compound with the 13,500 fold gain as compared to the co-crystal ligand. And also the researchers were able to get 6 novel crystal structure with this research. And most importantly, the whole process, right from the target identification until the experimental process, everything completed within 9 weeks. So this again shows uh, that how fast the SeeSar and the chemical space docking workflow is to come up with your own research projects. So with that said, that was the short introduction of the SeeSar workflow and the chemical space docking. Now let us quickly move towards the demo of it. If you have any questions, you can unmute and you can ask me. I hope you are able to see my screen.
Yes, your screen is visible, Dr. Faizan.
Okay. So this is the interface of the SeeSar. So once we enter into the new project, here you will be able to see different icons. As I mentioned, different modes. On the right side, you'll be able to see all the help section and the system settings, utilities, and everything. So quickly, I'll upload a protein. You can simply write the PDB ID and retrieve your protein from the PDB. So now you are able to see the protein in the 3D view. All I need to do is select the co-crystallized ligand. Here you will be able to see which is the co-crystallized ligand. And once I select it and I click the apply in the protein mode, now I have already defined the protein for docking and it is ready for docking within one click. So now what I'll do is I'll just take the same co-crystallized ligand and I'll add it to the docking mode. Now, as you're able to see, the icon is changed. Now we are in the docking mode and we have all three types of docking: standard docking, template-based docking, and covalent docking. For time being purpose, I'll just go with the standard docking because we don't have much time. Here, you'll be able to see different parameters coming for docking. We have the number of poses. So by default, it will be 10. But if you want more number of poses for each molecule, you can increase it up to 500. Then we have the clash tolerance parameter. So basically, if in case your binding pocket is too tight or too small, then in that case, what you can do is you can keep the clash tolerance on medium or high. Then we also have the option for allowing the ring conformation for the twisted form and for boat form. Also, we have the stereo centers, RS, EZ, and both. Again, if you want to add the pharmacophoric constraint to define your pharmacophore, or you can, in order to retain any sort of interaction, you can simply add any sort of pharmacophoric constraint. I'll show you. So if you want to add, for example, here I have this oxygen atom, and I know here the hydrogen bond is taking place. So in case if you want to add any pharmacophoric constraint, simply you can click here based on your preference. You are having here multiple pharmacophoric constraints for acceptor, donors, any carbon atom. And if you want to add your personalized, you can do it from here. So for now, I'll just add for the hydrogen bond acceptors and donors. And you can increase or decrease the size of the sphere, pharmacophoric sphere. And by doing so, you can add the pharmacophoric constraint. If you want to add multiple, that is also possible. Simply you can again define the new pharmacophoric constraint, and you can go for the docking. So I'll quickly show you the docking, and then we'll move for the inspirator mode. Meanwhile, if you have any question, you can ask. So yeah.
Dr. Faizan, there's some questions in the chat for you. I can read them for you if you'd prefer that, because I
Yeah,
know it's difficult for you to read the chat.
sure, sure. So yeah, you can read the questions. For now, let it be. I'll just go with the docking and I'll complete it, and then give me 2 minutes. So yeah, now we have already got the docking poses of the co-crystallized can be again docked. And here you will be able to see all different sorts of interactions, and then height-based scoring. In order to see what particular atom is showing the height-based scoring, all you need to do is you can click the L key from your keyboard and click particular atom like this. So here we have the green chromosphere, which is again showing the favorable interaction towards the binding pocket of the protein. And here we have the unfavorable atom, this carbon atom from the benzene ring. Here you will be able to see the height-based scoring is coming in positive 6.3 kilojoule per mole, which is unfavorable towards the uh, binding affinity of this ligand into the protein site. So in a similar way, you can select all these molecules and you can see hydrogen bond networks, torsion qualities, and all different uh, physicochemical parameters. And one thing to notice here, uh, unlike other scoring functions like glide scoring, dock scoring, the SeeSar provides you with a range of estimated affinity which comes from the picomolar to nanomolar range. So you are able to see here where your ligand fits with the estimated affinity. And then the ligand efficiency, intra and intermolecular clashes, and all sorts of different parameters comes in your results. I'll quickly take this molecule for the inspirator mode. Yeah, meanwhile, you can read the questions to me. I'll try to answer them.
Okay, I'll read the first question. Compared to
Sure.
brute force virtual screening, where do you see the biggest efficiency gains in chemical space docking, in computation time or hit quality?
Both computational time as well as hit quality. Meanwhile, if you use the brute force docking, the computational cost will increase a lot, and at a certain point, it will be a kind of computational burden. Because if we go beyond million molecules, it will be, first of all, time consuming, and again, if you get some results from it, the question arises how you will filter those molecules and come up with the best selection. In case of chemical space docking, each and everything is generated during the fly. All the fragmentation, what do you say? The chemical space docking, in the anchoring step, we take the synthon, then subsequently in the first extension and second extension, uh, those fragments are joined and come up as a single molecule in the binding pocket based on the size and shape of your binding pocket. So now you can imagine, uh, in the brute force docking, you're coming up with the enumerated molecule and docking the same. But in case of chemical space docking, you're designing the molecule in the binding pocket of the receptor, which is again the tailored fit. So whatever the molecule you are getting, it is synthetically feasible to you, or else you can simply purchase it from the vendors. I
Thank you.
hope I answered your question.
I'm seeing that Dr. Raghu has already gone ahead and answered a few questions in the chat, but it would be great to get an answer from you as well, Dr. Faizan. So I'm going to read the questions.
Okay.
With the known protein structures, we should have a finite number of synthons. Thus, there should be limited groups of molecular binding options. Can we group such molecules to speed up further?
Mm, can you ask the question again?
With the known protein structures, we should have a
Mhm.
finite number of synthons. Thus, there should be limited groups of molecular binding options. Can we group such molecules to speed up further?
Like in case if you are asking for the template based talking.
Well, this is not my question, so we'll have to wait for Dr. Shwetan to answer that in the chat. But Dr.
Okay, let me
Raghu
read.
has answered saying, no, the synthons are limited. The synthons are reagents which can interact with the scaffolds.
Yeah, we are using the synthon as the first step, anchoring of these synthons. And no, these are not finite numbers. We have, as you have seen, the library is gone to trillions and even septillions of molecule. So whatever fits best will be taken further, and we can choose from those synthons, and we can take it further, first extension and second extension.
Okay. Next question is, does this method follow the binding affinity for the top ligand selection?
Yes, as I showed here, also you will be able to see the estimated affinity, estimated binding affinity. It comes in a picomolar to micromolar size scale. So wherever your molecule fits in, it gives the lower and upper limit of the estimated affinity in your results.
Right. Next question is, do you see chemical space docking eventually replacing traditional virtual screening, or do you expect them to remain complementary approaches?
Uh, we can't say that it replaces the traditional virtual screening, because it is, again, I want to mention that one more time, that it is not changing the principle of the traditional docking. It works with the same principle, but only the pattern here is how we introduce those fragments of the molecule in the binding pocket and how efficiently we come up with the results.
Okay. Um, Next question is from Saurabh. He says, would blind docking work better than other docking methods, as there's an involvement of many molecules with random spaces, such that we can also get hidden spaces in the protein, and we can screen on the basis of those pockets.
Okay. So due to time constraint, I couldn't show you one of the feature of our SeeSar. As you can see here, we have the binding site identification. So usually, people does the blind docking in case when they are not sure about the binding pocket, right? So in order to find the binding pocket, they does the blind docking, but the binding site uh, mode that we have in the SeeSar with the dock site score algorithm quickly within a second shows you whatever available binding or the druggable pockets are present in the protein. So with that itself, you can go for the standard docking. You don't have to again keep on searching with the blind docking because it will show you the best druggable pocket.
All right. There's a follow-up question from Dr. Shwetank. Can we group synthons since there are a finite number of scaffolds?
Can we group synthons? So basically, we select synthons and we can select multiple synthons coming from the anchoring of synthon first step, and we can take those further for the first extension and second extension.
Okay. Is SeeSar freely available, or do we need to purchase the license?
No, it comes with a user license, and as already Dr. Raghu mentioned that for the academics, it is quite affordable as compared to the commercial license. So you can reach out to us and we can have thorough discussion. Also, I can show you the presentation and demo in much uh, good way. So
Okay.
if questions are over, I just want to quickly show the inspirator mode because as I said, it is the powerhouse for the ideation. So within few clicks, you'll be able to design the molecules based on the medicinal chemistry rules.
Yes, Dr. Faizan, please go
For,
ahead.
for 2 minutes, we'll pause the questions. Then again, I'll take back if any questions are there. Okay. So here we have the inspirator mode. So already I have added this particular ligand, which was the co-crystallized ligand in the inspirator mode. And it comes with 4 different options. First, we have the core replacement. Then we have the linking and merging. Then we have the growing and the analoguing. So now the analoguing is visible. Let us go with it and we'll see what kind of results it's giving. So within a couple of seconds, it generates the analog for the ligand which you have given as a query molecule. I'll select all these molecules and I'll estimate the binding affinity and let us see if we get any better results as compared to the co-crystallized ligand. So here all different molecules are coming. So you are able to see where the analog has been added, where the new functional group has been added. So this was our co-crystallized ligand. And here we have the analog with one additional amino substituent. And with that itself, you can see here the estimated affinity of the molecule have come down to picomolar range, right? So, and this happened within one click. We already got 10 different results. Okay. And again, if you want more, you can keep it up to 500 at a time. Okay, this was the analoging in the inspirator mode. Uh, I'll delete all this and let us see for other options what we have here. I'll add the extension exit vector over here at this particular position. I hope you are able to see my screen. So as I have added the exit vector at the particular position, the part of this molecule which is faded will again be replaced in the binding pocket itself. So you are able to see in the 3D view itself. So now we have got the option growing. If we click the molecule from where we have added the exit vector, from that particular position, the molecule will go inside the binding pocket. So yeah, we already got 10 results. So these are all the other molecules coming from the inspirator mode. So as you are able to see, these are all novel molecules coming from the growing option. Again, quickly I'll delete all these and let us now try to change the core of this molecule. For this, what I'll do is I'll add two different exit groups, exit vectors. So now the core of this particular molecule is faded, right? So by this, we can be able to replace the scaffold of this molecule. Here you are able to see in the 3D view also, right? So now we can replace the so yeah, we have got 10 different results. As you can see here, these all are coming from the inspirator mode after replacing the scaffold. And all of this is happening inside the binding pocket. Let me show you. This hole is a binding pocket of the protein. I'll add the surface here so that it will be uh, visible to you. Meanwhile, I'll take the other questions as well. So yeah, so this is the binding pocket. So whatever the molecules are generating in the inspirator mode are generating based on the size of the binding pocket. Yeah, if you have any questions, we can continue with the questions.
Okay, Dr. Faizan. We only have a couple questions left. This is from Dr. Shwetank once again. Can we test multiple proteins, say, generated by a specific cell type under a specific condition with multiple sensons?
Checking multiple proteins with multiple synthons.
Mm-hmm.
First of all, we can do the traditional docking with large libraries using this SeeSar also. So in that case, you can check with the enumerated molecules, or else with the multiple synthons using, like at a time, the single protein can be used here.
All right. This is from Satswika. Does SeeSar work similar as Discovery BioVia Studio?
Uh, yeah, it works similar, but as I mentioned, that we gets the estimated affinity into the picomolar to micromolar range. Also, the height-based scoring that we have is kind of much more closer to the real delta G, which is again the real values which we are looking when we are seeing the binding affinity of the ligand in the binding pocket of the protein.
All right. Thank you, Dr. Faizan. That covers all of the questions. Yeah, thank you to all the professors who have spoken thus far, Dr. Gitanjali Yadav, Dr. Narendra Mehra, Dr. Raghu, and Dr. Faizan. We will be taking a break, a lunch break now, and coming back at 2:30 p.m. Indian Standard Time.
Thank you, everyone. Thank you for the opportunity.